So let's take another example of full factorial design experiment. In this case, I have 4 factors instead of 2, and see what is similar to the previous example and what can be actually different. Well, in general, if we talk about the 4 factors full factorial design, you can see that this is the design matrix that I have, and you can see that it gives you 16 trials. So 2 in the power of 4, it's 16, and it's exactly the number of trials you have, right? And that gives you the first advantage. If you use 4 factors, you don't need any replicates because you have already enough degrees of freedom to estimate all effects. And we will discuss how many effects you can estimate in a minute, right? And then the contrast matrix will be huge. For example, this is a full analysis matrix, not just a contrast matrix, but analysis matrix where I have only the main effects. So I have 4 main effects, right? Then I have also 6 two-factor interactions. So I have 10 effects in total to estimate, so the number of effects is 10. And then I also need 1 degree of freedom to estimate the average, the ground average. So this is how many I need for effects, and this is for ground average. So I need 11 degrees of freedom to estimate everything that I need, right? But initially I have 16 degrees of freedom. So it means that I can use 5 degrees of freedom for residuals, for noise, right? And that's good. So that's what I mean by saying no replications are needed. So you already have enough degrees of freedom to estimate all potential sources of systematic variation. It means 10 effects, the ground average, and the 5, you still have 5 left for estimation of error, which is more than enough. So you don't need any replicates in this case. Okay. And to remember that where all these 5 degrees of freedom came from, they came from these 3-factor interactions and also the 4-factor interactions. So although we don't have replicates, we can use the data from these 5 effects, 5 interaction effects, and we know that this is noise, right? So we know that most of the time the 3-factor or higher number of factor interactions is just noise, and we will use these to estimate the value of our noise. So that's the biggest difference here, no replicates. Now let's see how it works. Well, first of all, let me introduce the case. In this case, I also have the reaction, chemical reaction, or it's a process, an industrial process, where I change 4 factors. It's the catalyst charge, it's the temperature, it's the pressure, and the concentration of catalyst. And then you can see that, again, I have 2 levels for each, minus and plus, and then you can see the levels here in the table. This is the design matrix encoded values plus all the measurements. So this is the outcome, and the outcome is still yield. So this is the yield I got in every run. And in this case, I have as many runs as many trials. And then if I make a cuckoo plot for the yield, for the outcomes, you can see again that I don't have any outliers or any other strange behavior. So from that point of view, it seems like the process went well, right? The experiment went well. So now let's analyze this data. And this is how the data looks like in my spreadsheet software. So you can see that I use the abbreviation for the column names, and I'm going to use them also in all my models, right? And also you can see that in this case, in spreadsheet at least, I have the real values for every level. That's much easier when you indeed need to run the experiment, so you know at which temperature, for example, you work and which pressure you have to set and so on. Okay. Now, the first thing I did in this case, I computed all effects, all 15 effects, and then you can see that I use, sometimes I will use numbers, sometimes I will use letters, but the idea is that the first is the catalyst charge, then we have temperature, then we have pressure, and then we have the catalyst concentration. Then, for example, 1, 2, it's an interaction between first 2 main effects, first 2 factors, it's a catalyst charge and temperature. Then, for example, 2, 4, it's an interaction between the temperature and the catalyst concentration, right? Then you can see that most of the effects are quite small. So you can see these are very small effects, and you remember this is like a level of noise, right? And then you can see very few have a higher. For example, this one is higher, this one is a little bit higher, this one, yeah, so, and this is significantly higher, very, very large. So probably this effect is significant and also quite large here. Okay, so we can already see, sort of compare the magnitude of the noisy factors, of the noisy effects that we already know that in advance that they are noisy, and then the effects that are expected to be systematic, at least some of them. Okay. Now let's do the analysis. And first of all, how to calculate the standard error. You remember that in the previous example, we had replicates, and we used replicate runs to estimate standard error. We simply took a variance for every trial, we have 2 runs, and then we took variance for outcomes of these 2 runs to estimate the standard error. But in this case, we don't have replicates. How to calculate standard error in this case? How to calculate the variance of noise in this case? Well, the answer is simple. We know that this is noise. So it means that variation of these values is actually the noise variance, right? So how we can compute the variance of noise? So in this case, so first of all, we double it. So you can see minus 1.5, 1, and so on and so forth. And then we take a sum of squared values for these doublet values. So that gives us the sum of squared values of 6. And now we can compute a Pullet variance by simply taking an average of this, right? So this is our Pullet variance. Okay. And now we can compute, for example, standard error. We know that for effect, we have 8 values at one level, 8 values in the second level. The variance for every level is the same. We assume that the variance will be equal, so we can use the Pullet variance in this case. And then we do the similar calculations that we did before. So this is our standard error of effect, right? However, we can do the same calculations in a simpler way, right? So what do I mean by that? I mean, we know that this is already the noise. So why not to compute standard error of these values? So instead of doing this, effect to variance and so on and so forth, we know this is the variation of the noise. And we know that average is 0 because average for noise is always 0. So we don't have to compute average in this case. We know in advance it's 0. So we actually can keep 1 degree of freedom, right? So we don't lose any degrees of freedom here. So if we have 5 values, how we compute variance of 5 values? We simply take a difference between these values and mean, but mean is 0, so it means that we simply take a sum of squared values of this one, and then we divide it to 5, right? So this is exactly the variance of my standard error, right? Not variance yet, it's just a sum of squared values. We need to divide it to 5 to get the variance. So this is the variance of my standard error, and square root of this will give me the standard error, which is identical to what we had before. So just 2 different ways, 2 different representations of calculating standard error. This one, I think it's simpler. So, but in this case, we don't need to do it manually because ANOVA will do it for us. And in a minute, I'll show you that the results will be also identical. Okay. But this is just an intuition. So when we don't have any replicates, we use interactions with 3 factors or more to estimate the noise level, to estimate this, how big the noise is. Now let's do ANOVA. And first of all, you can see that I use this long way to make the ANOVA analysis. I have 4 main effects, and then I explicitly specified all 6 interactions. And I use the data from my spreadsheets where I have the real values, the real levels. And that's the outcome of ANOVA, right? So you can see that these 2 effects are significant. So it's these 2. This effect seems to be also significant. And then you can see that this is between C and T. You remember that C is a number of 4 in this case, and T is a number of 2, so it's 2, 4. It's exactly this one, right? Then you can see, for example, in this case, the p-value is 0.07. So strictly speaking, we do not reject null hypothesis here, and it's exactly this one that we had doubts about, right? So it's 125, so it's a bit larger than this one, but it seems not to be large enough, not to be extreme enough. So we identify it as a significant effect, right? So you can see from that point of view, ANOVA results are very similar to our own preliminary considerations, right? And then the residuals, again, you can see we get absolutely the same value that I used before. So we have sum of squared value 6. We have 5 degrees of freedom. So this is the Pullet variance 1.2. So it's identical to all our calculations. And then we can use this 1.2 to estimate the standard error, which is, we already know, it's 0.55, right? Now look. Because we have so many possibly systematic effects and also random effects, in this case we can use another tool which was not actually available for us when we use only 3 factors. And this tool is cuckoo plot for the effects. And that's very interesting because now we know that only 4 out of 15 effects are not noise, right? So are significant. It means that all this is noise, all this is noise, all this is noise. And we know that noise is distributed normally. So what it means? It means that if we make a cuckoo plot, which you remember that we use for checking the normality of our data, most of the values, I mean cuckoo plot for the effect values, most of these values will follow normal distribution, that they will lie along this ideal line. and only 4 do not follow normal distribution, and we will see these 4 as outliers. And this is what do I mean by that. In this case, I use letters instead of numbers. So A, it's effect number 1, it's a CC. Then B, it's number 2, it's a temperature. C is 3, it's a pressure, and then D is 4, it's the catalyst concentration, right? So you can see that most of the effects are noisy, and therefore they follow the normal distribution, right? And only 4 effects deviate from this trend, right? It's effect A, which is the catalyst charge, and you can see it's negative, right? It's effect D, it's the concentration of the catalyst, this one, also negative. Then you can see effect B, a very far away, and that's the biggest effect that we have. It's a temperature. And then it's the interaction effect between B and D, and that's exactly what we have here, right? So in this case, the Cuckoo plot can be a very nice visual representation of which effect are actually significant and which effect are noisy. Okay, so this is kind of an extra visual tool to estimate the importance of your effect. Okay, the main effect plot, well, it's just the same plot that we had before. We can also compute the confidence intervals, and then you can see that in this case, the confidence interval is approximately, it's pretty narrow, right? So it's like plus minus maybe 1.4 or maybe 1.3, something like this. Okay. Then you can see again, so we have clear effect here. We have very clear and large effect here. This is completely inert factor. It means the effect is almost 0. And then you have a small negative effect in this case, right? Now the interactions, in this case, we know that there is only one interaction, which is significant. Therefore, there is no reason to show all this big plot with all possible interactions. I just show the interaction for this particular case. And then I also show the confidence interval for this interaction. And then you can see interesting things. So the temperature and the yield indeed interact. But you can see that, for example, if you use temperature at 240, you can see that yield, not yield, of course, the temperature and the concentration of catalyst, right? You can see that the yield, the average yield, does not depend on the concentration of catalyst. They are more or less the same. Yeah? But if temperature is low, 220 degrees, then you can see that this concentration of catalyst gives you a smaller yield than this concentration of catalyst. Okay. So from that point of view, you can see that actually 10, if you use concentration of catalyst 10, it seems to be the best choice in this case. But if you want to continue and go beyond that, it's important to follow this interaction, because maybe they will cross at some point, and then the concentration of catalyst, which is 12 or higher, will be actually beneficial in this case. Okay. So this is actually it. Not so much new things, but just more or less the same approach. We also remember that we need to test if we need to validate our ANOVA model. So first of all, we look at the residuals. Again, we use a Cuckoo plot for residuals and also make a Shapiro-Wilk test for normality. And it seems to be all okay. And then finally, we make also the test for the homogeneity of variance. I make a visualization, how variance, the variation of the residuals look like depending on the level of every of the 4 factors. Seems to be more or less the same. And then the p-value for the variance test is also quite large. So in this case, we sort of, again, seems to be ANOVA results are reliable enough. Okay. So that's it about this case, and we can conclude on full factorial design. So full factorial design, usually it's based on 2 levels, because you just use it for variable screening. You don't use full factorial design for optimization. It will be too many trials. But for 2 levels, for variable screening, it seems to be a very efficient way to do the variable screening, right? It gives you estimation of main effects. It gives you estimation of interactions. All effects are not confounded. And then it's a balanced design, so it's perfect for ANOVA and Tokyo analysis. We have many well-known tools for analyzing your results, but however, there is one drawback in full factorial design. You remember that the number of trials is doubled every time you add a new factor. For example, if you have 2 factors, you know that you have 3 systematic effects, right? Possible effects. It's the 2 main effects and 1 interaction. So it's 3 systematic effects. You remember you always need +1 for average, +1 degree of freedom. And then you also need approximately 5 degrees of freedom for the noise, right? And then you can see that here you have 3 effects. Then you need 1 more for average. and then you need some noise, also for some noise, but you have only 4 trials. So in this case, full factorial design with one replicate will not be enough to estimate all effects statistically. So in this case, you need to add some replicates. So 4 trials is not enough. Okay. However, if you have 3 factors, in this case you have 6 effects, and then you also have one for the average, so it's 7. It means that you always have one left for estimation the noise, and it's a 3-factor interaction. So in this case, the number of trials will be just enough. Of course, in this case, the noise estimation of noise will not be very good, because the noise can be potentially large, but still it's doable. So strictly speaking, you don't need replicates in this case. Okay. If you have 4 factors like the previous example, we have 10 potential effects, potential systematic effects. And then you remember that this is the perfect case, right? So because we have enough degrees of freedom for all effects and also for reliable estimation of noise, we have 5 degrees of freedom for noise. So this is very good. Now, the problem starts with 5 factors. You can see in 5 factors, you have 5 main effects and 10 interactions, 2-factor interactions. So you need 15 degrees of freedom plus 1 more for the average, and then plus at least 1 or better 3 or 5 for the noise. So it means that you need approximately maybe 19 degrees of freedom, but you have 32. So this is huge, right? So it means that you start wasting your time and resources because you have much more trials than you actually need. With 6, it's even worse. You can see you have 21 effects, plus 1, it's 22, plus maybe 3 for error, it's 25, but you have 64. So this is really bad. So now it's a wasting of resources. So strictly speaking, full factorial design is good enough if you have up to 5 factors. Even for 5 factors, it's already became redundant, but up to 5 factors, it's good. But after that, if you have 6 or more factors, full factorial design is redundant. It requires much more trials than actually you need to estimate all the effects. What to do in this case, that's the matter of the next learning sequence, which is a fractional factorial design. But before that, we are going to have several videos on R, how to do things in R. There will be much more videos than in the previous blog because we have to cover a lot of things. You remember, we write our own toolbox. So I will tell you how to actually make a design matrix, how to estimate, how to make nice plots for the effects, and how to do a lot of other things. So let's continue with our sessions.